harmonic motion is one of the most important applications of differential equations. And I won't be too specific about the definition of harmonic motion here. I basically just mean something that is regular and repetitive. And there are really amazingly interesting things that involve harmonic motion, things like earthquakes, things like biological macromolecules. And so I don't want you to think that all harmonic motion is like if you take a metal spring and attach it to a mass. It's so much more than that. And yet, for pedagogical purposes, what I'm going to do is start with just a really simple spring mass system. So there's a wall over here and a floor over here, and there is a mass of mass m. That's attached to the wall by a spring characterized by a spring constant k. That's an inherent property of the spring that we'll say a little bit more about in a moment. And perhaps between the mass and the floor, there's some frictional damping characterized by this constant Greek letter gamma. And when the spring is at its natural length, meaning like no one has artificially compressed it or extended it, you're just sort of letting it be, we're going to call the position of the mass, the position of the center of the block, x equals 0. In order to model this problem, we have to take account of the forces acting on the mass, and in this case, we're just interested in the horizontal direction. And really, there are possibly three forces, and the main one, most important one, arguably, is the restoring force, also known as the spring force, and this is the thing that's caused by the spring. And if it's what's known as a Hookean spring, or sometimes a linear spring, then this force is minus kx, where k is a positive constant. So think about what this means. If you increase x by pulling the mass to the right, then the force acts oppositely that, right? Minus kx, that'll be a negative number. There's a negative force on the block that causes it to want to accelerate back to the left. On the other hand, if you compress the spring by pushing it to the left, then you've made x a negative number, because you've put it to the left of the equilibrium. So negative kx here is a positive number. That's a rightward force that causes the mass to want to accelerate to the right. So in short, the spring force opposes the displacement of the block. And this is called a Hookean spring when it's directly proportional to that displacement. And you could have more complicated kinds of springs in which it's not minus kx, but minus maybe something more complicated involving x. Also, there's frictional damping. Frictional damping doesn't oppose the displacement of the mass, it opposes the velocity of the mass. And if the position is x, the velocity is x dot. And so a simple model for the frictional damping is that it's minus gamma x dot, where gamma is a positive constant characterizing the strength of the friction, right? So what that says is that if the velocity is to the right, if the block is currently moving to the right, friction wants to drag it to the left. If the block is currently moving to the left, friction wants to drag it to the right. And then there could possibly be some external force acting on the system, and I haven't drawn one here, but you could have a person who's periodically pushing on the block or something like that. And we're going to model this with Newton's law, and Newton's law says mass times acceleration is the sum of forces, and a way of writing mass times acceleration is m times x double dot. So remember, the dots represent derivatives, and the second derivative of position is acceleration. So this is mass times acceleration equals, and then we just write in the forces. So this is the spring force minus kx, the damping force minus gamma x dot, and our external force f of t. It's common to bring all the terms involving x to the left-hand side, so we get this equation here, mx double dot plus gamma x dot plus kx equals f of t. And you'll notice that this is a linear constant coefficient differential equation, potentially with an inhomogeneity here on the right-hand side. And so this is, this topic of harmonic motion is very relevant to linear differential equations, and if you know techniques for solving linear constant coefficient differential equations, you can apply them to solve this problem. All right, thanks for listening.